Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at a special type of discrete distribution known as the binomial distribution. So the binomial distribution is the distribution that occurs when you have multiple Bernoulli trials. Bernoulli is just the guy who came up with it. So a Bernoulli trial has two possible outcomes, success or failure. When you perform multiple independent Bernoulli trials, you have a binomial distribution. So when we're talking the binomial distribution, n is the number of trials and p is the probability of success on each trial. This is what independent means. It means the probability of success doesn't change from trial to trial. Now note here, when we're using the binomial distribution, if it's about picking something, it needs to be picked with replacement. If it's picked without replacement, it's another distribution called the hypergeometric. So here our random variable x is the number of successes, and we write it like this to say x follows a binomial distribution. So when we write this, we include in the brackets the two numbers. The first is the mean, n times p, number of trials times probability of success. The second number is the variance for this distribution. It is n times p times 1 minus p. So we saw in a previous video that we can write down tables and list all of the probabilities for each possible outcome. But when we're dealing with a binomial distribution, sometimes x can take on heaps of different values. If you do 100 trials, for example, x could take on any value, any whole number between and including 0 and 100. It would take far too long to draw a table. Instead, we use what's called the probability mass function. This helps us calculate the probability. What we do is input a value here into this function, and it tells us the probability that that number of successes occurs. So the probability mass function starts with this term here. This is n choose x. You may have seen it written like this or this, and this is p to the power of x times 1 minus p to the power of x. All right, again, hopefully this will be clearer when we do an example. So let's say from a normal deck of 52 cards, I choose 10 cards, one after the other with replacement. Calculate the probability that I pick exactly 5 hearts, and we'll also calculate the mean and variance. So here our random variable is the number of hearts. So x has to be a whole number between and including 0 and 10. You can't pick, say, 3.5 hearts. So we can see that x is discrete. Now the reason it is binomial is because each time I pick a card, it is a Bernoulli trial. I can either pick a heart, success, or not pick a heart, failure. So in this way, there are two possible outcomes each trial. So we can use this function up here, the PMF, to calculate the required probability. So what we're trying to calculate here is the probability that our random variable number of hearts is equal to 5. So the probability mass function tells us this will be n. So n here is 10 because there are 10 trials in total. X is the number of successes I want, so 5. Now p is the probability of success on each trial. In a normal deck of cards, there are 52 cards, 13 hearts. Or in other words, there are 4 suits: hearts, diamonds, spades, and clubs. Hearts is one of them. Each time I pick the card, the probability of picking a heart, the probability of success is a quarter. Because it's with replacement, that probability won't change. Every time I pick a card, I have a 1/4 probability of picking hearts. So that is p, 1/4. X again is 5, so 1/4 to the power of 5. And then we do 1 minus 1/4 to the power of 5 as well. So if we put that in our calculator, we get about 0.146. So there's about a 14.6% chance that I will pick exactly 5 hearts. Now, the expected value is just n times p. So n is 10, p is a quarter, 10 times a quarter is 2.5. I expect 2.5 hearts. Of course, that's not actually possible to get a half number of hearts. But what it means is if I performed this experiment many times, on average, I expect that I'd pick 2.5 hearts each time. So that's the expected value. The variance is n times p, which we just calculated as 2.5, and then you times that by 3/4, by 1 minus p. So the variance here would be 10 times 1/4 times 3/4. It would be 1.875. And if we were asked for the standard deviation of x, it would just be the square root of that. All right, let's now look at the CDF. So CDF stands for cumulative distribution function. It calculates the probability that our random variable is up to and including a certain value. So let's return to the example on the previous slide. 52 cards, I'm going to pick 10 with replacement. Let x be the number of hearts. So here this says, what's the probability I pick 4 or fewer hearts? So to do that, we would have to do the probability that I pick no hearts, then I'd have to calculate the probability I pick 1, and then 2, and so on, all the way up to 4. That takes a long time, and you can see that if this was like 100 trials, and I wanted to calculate probability of 30 hearts, it would just take far too long. That's why we need the CDF. So the CDF has already been thought of by many people. You can usually go online or from a graphics calculator, calculate it from that. So you go to this online calculator and you input n, p, and x, the number of successes you want, into the CDF, and it will tell you the probability of being up to and including that value. So the output will look something like this, and you should get 0.9219, thereabouts. So there's about a 93% chance you get 4 or fewer hearts. What if I wanted to calculate the probability x is greater than or equal to 3? Well, the CDF only calculates the probability up to and including a value, not more than a value. So how would I do this? Well, if I want to calculate probability x is greater than 3, note x can take values 0, 1, 2, 3, 4, all the way up to 10 in this particular question. So what I'm asking for is this. I want to calculate those probabilities, but the CDF can only calculate something like this. But of course, all of these probabilities add to 1. So what I can do here is I can input into the CDF, again, n, p, and this time my x will be 2. This circled in red is what this calculates. So if I subtract this from the whole, which is 1, I'm left with black, which is what I wanted. And I should get an answer of about 0.4744. So I'm going to do something here. Here I want to calculate the probability that the number of hearts is between and including 3 and 7. So again, these are the possible values that our random variable can take. I want this here. But of course, the CDF doesn't calculate this directly. How can I come up with this? Well, what I can do is I can take this here and I can subtract this here. So putting this on a calculator, I get 0.99958. Putting this on the calculator, we get 0.52559. So subtracting them, we get about 0.474. All right, let's now finish with a question involving the mean and variance. So here we're told x follows a binomial distribution. This is the expected value. This is the variance. We want to find the probability x is less than 30. Now we can't possibly find probabilities in a binomial distribution unless we find n and p. So that's got to be our first goal here. Now we know the expected value of a binomial distribution is NP. So we're told that equals 37. The variance is always NP times 1 minus P. So we're told that that variance here is 9.62. So how do I solve these to recover N and P? Well, what I can do is I can divide the top equation by the bottom. So on the left-hand side, I can cancel out the N's and P's. So I'm left with, on the left-hand side, 1 minus P. On the right-hand side, 9.62 divided 37 is 0.26. So we can solve that easily and find that P is 0.74. So that, of course, means if I substitute back up into this one, that N will be 37 divided 0.74, which is 50. Now that I know N and P, I can calculate probabilities using the binomial distribution. Now, because I'm not after the probability of a specific value, I won't use the PMF. I will use the CDF. Use the CDF when you want to calculate the probability over a range of values. Now, because x can only take whole number values, the probability of being less than 30 is the same as being less than or equal to 29. So putting that on the calculator, we get about 0.01. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.